All right, today we are going to unlock the absolute fundamentals of chemistry. This is the science that explains pretty much everything: the materials, the incredible transformations, and all the energy that shapes our entire physical world. So let's dive right in.
So what is chemistry at its heart? Well, it's really the study of matter. The actual stuff that makes up the universe. We're going to explore its properties, the changes it goes through, and, super importantly, the energy that drives all those changes. Think of these four things as our roadmap for this whole journey.
Okay, here's our game plan. We're going to build this thing from the ground up. We'll start with the essence of chemistry, then get into matter in motion and change. After that, we'll talk about the scientific mindset itself, how to think like a chemist. Then we'll get practical with the language of measurement, quantifying the world, and finally wrap up with how we talk about certainty in science.
All right, Section 1, the essence of chemistry. First things first, right? We have to get our vocabulary straight. We've got to be crystal clear on what we mean when we say matter, what defines its composition, and how we actually describe its properties.
Okay, so one of the most crucial distinctions you have to get is the difference between physical and chemical properties. A physical property is something you can see or measure without changing the stuff itself. Think about the blue color of copper sulfate, or the density of lead, right? You're just observing it. But a chemical property, well, that only shows up when the substance actually transforms into something else, like how flammable gasoline is, or the fact that iron rusts. You don't see those properties until a chemical change is happening.
So that brings us to our next section, matter in motion and change. Now that we know about properties, let's look at the two big ways matter can change, physically and chemically. And you'll see these changes are tied directly to the properties we just talked about.
And this image, this is a perfect illustration of the difference. Over on the left, you've got ice melting into water. It's changing its form from solid to liquid, but the H2O molecules, they are exactly the same. That's a classic physical change. But look at the right. Here, an electric current is ripping water molecules apart into totally new things, hydrogen gas and oxygen gas. The actual composition has changed. That is a chemical change.
Okay, let's run through a few examples to really nail this down. Frost forming? That's just water vapor becoming ice, so physical. A cornstalk growing? Oh yeah, that's tons of complex reactions making new plant stuff, definitely chemical. A match burning? Classic chemical change. What about sweat evaporating? That's just liquid water turning into a gas, so physical. And silver tarnishing? That's silver reacting with sulfur to make a totally new compound, silver sulfide. So it's chemical. See the pattern? The big question is always, did it turn into something new?
And of course, these changes are all tied to the three states of matter: solid, liquid, and gas. If you zoom all the way down to the particle level, it makes perfect sense. In a solid, the particles are all locked into a neat, organized structure, just vibrating in place. In a liquid, they're still close, but they can tumble and slide past each other. And in a gas, well, they're super far apart, just zipping around randomly. A substance's state is one of its most basic physical properties.
So what's the driving force behind all these changes? It's energy. And for our purposes, we can think about energy in two main flavors. You've got potential energy, which is basically stored energy. Think of a stretched rubber band or the chemicals just waiting inside a battery. Then you have kinetic energy, which is the energy of motion. The really cool part? These two can be converted back and forth into each other.
Just look at these examples here. That raised weight, it's packed with potential energy just because of where it is, up high. Let it go, and what happens? It falls, converting all that potential energy into the kinetic energy of motion. It's the same idea with chemistry. The molecules in fuel have a ton of stored chemical potential energy. When you burn that fuel, they rearrange into more stable things, like exhaust gases, and release that stored energy as heat and the motion that makes a car go. This is a huge theme in nature. Systems tend to move from higher, less stable energy states to lower, more stable ones.
Okay, so understanding these concepts is one part of the puzzle, but investigating them, that's a whole other skill. And that brings us to Section 3, the scientific mindset. This is all about the intellectual toolkit a chemist uses.
Look, science is not just a big book of facts. It's a process. It's a way of thinking. It all starts with an observation, seeing something interesting. That leads you to form a hypothesis, which is really just a testable explanation. Then you design experiments to see if your hypothesis holds up. The results of those experiments help you build a model or a theory, but it doesn't stop there. That model gets tested with even more experiments, which leads to revisions and refinements. It's this continuous, evidence-based loop, and honestly, it's the most powerful tool we have for figuring out how the universe actually works.
And this same rigorous mindset applies directly to problem solving. You know, a good chemist never just jumps straight into the math, no way. First, you really have to stop and analyze the problem. Then, you make a plan, a strategy. You might even draw a little map of the steps you need to take. Then, you can actually solve it. And when you're done, you check your work. Ask yourself, does this answer even make sense? And maybe you'll even add a comment about it. Seriously, the planning and the checking are just as important as getting the number right.
Right, on to Section 4, the language of measurement. To test any of our ideas or solve these problems, we need data. And getting data means making measurements. So let's talk about the universal language scientists use to quantify the world around them.
This is what we call the SI, or the International System of Units. It's basically a standardized set of base units for all the big physical quantities. So mass is always in kilograms, length in meters, time in seconds, and temperature in Kelvin. Why does this matter? Well, using a common system means that a scientist in Japan can understand the results from a scientist in Brazil. No confusion, no ambiguity. It's the language we all agree to speak.
So, let's say you're faced with a big, messy problem, like figuring out the mass of a transatlantic cable. How do you even start? Well, like we said before, you don't grab your calculator, you make a plan. And this flowchart is a perfect example of that plan. It's a roadmap that takes us from our starting point, length in kilometers, all the way to our final answer in kilograms, one logical step at a time.
And here's where the plan comes to life. We use a really powerful technique called dimensional analysis. All we're doing is stringing together conversion factors to systematically hop from one unit to the next. The best part is, it's almost foolproof, because if you set it up right, the units guide you. See how the kilometers cancel out, then the meters, then the pounds. It all just works, leaving you with exactly the unit you wanted at the end. Kilograms per cable.
Okay, Section 5, quantifying the world. Let's zoom in on one of those key measurements we just mentioned, temperature. We all know what hot and cold feels like, but scientists need to be way more precise, and they use 3 different scales to do it. So, you've probably heard of all 3 of these scales. There's Fahrenheit, which is common in the US, then there's Celsius, which is used pretty much everywhere else, and in all science labs. Both of those are based on the freezing and boiling points of water. But the really fundamental one for science is Kelvin. It's an absolute scale. 0 Kelvin is absolute 0. You literally cannot get any colder. And that's exactly why it's the official SI unit. And the good news is, we can switch between these scales pretty easily using these formulas. For instance, if you have a body temperature of 38.7 degrees Celsius, you just add 273.15 to get it in Kelvin. Easy. And if you want to know if that's a fever in Fahrenheit, you just plug it into the other formula, and yep, that comes out to 101.7 degrees. Being comfortable moving between these scales is a super important skill.
All right, our final section, certainty in science. Let's talk about what I like to call the craftsmanship of measurement. Because look, a result is only as good as the numbers you use to get it. This is where the absolutely essential ideas of precision, accuracy, and significant figures come in.
So how do we communicate how certain we are about a measurement? We use something called significant figures, or sig figs. There are a few rules. Zeros at the beginning, like in 0.05, are never significant. They're just placeholders. So that's just one sig fig. A 0 trapped between other numbers, like in 205, is always significant. So that has 3. And zeros at the end are only significant if there's a decimal point. So a number like 5.00 tells you it was measured very precisely, and it has 3 significant figures.
And this target visual is the absolute best way to understand 2 other critical ideas, precision and accuracy. They are not the same thing. Precision is all about reproducibility. See how close together the shots are in targets A and B? That's precision. Accuracy is about how close you are to the actual bullseye, the true value. So target A is what we're always aiming for, both accurate and precise. Target B is precise, but it's not accurate. This suggests a systematic error. Maybe the scope on the rifle is off. And target C? Well, that's just random error. The shots are all over the place. But hey, their average is kind of close to the center. So there you have it. The real keys to studying chemistry aren't just memorizing formulas. They're about deeply understanding a few core concepts. What matters is how it changes, the energy that drives it, and most importantly, the rigorous, logical way of thinking you need to investigate it all. So the question I'll leave you with is this. Now that you have these keys, how are you going to use them to start unlocking the much more complex and fascinating chemical world that's out there waiting?